on 12.1, 12.2, or 12.3 material? Most of you are saying it's not hard, just time consuming. Just take some time to do it. Today we're going to continue on with 12.4. And 12.4 may be a little different than what you guys have done in the past, and it's a measure of variance. How much does the data points vary from each other? So we're going to talk about really kind of three ways to calculate variance. The first way is going to be the range. You know, if I have a range of 50 points or if I have a range of 10 points, it gives me an idea of, it's the easiest way to calculate the variance, the range. And then from range, we can get a better idea of variance, or a better idea of how much these data points change from one another by calculating the variance and the standard deviation. The standard deviation is the square root of the variance. So if you find variance, you can just hit the square root button in your calculator and that will give you the standard deviation. So they're kind of the same. One, we're going to use standard deviation, we're going to use a lot in the next two sections. And then the last thing we're going to do is we're going to interpret what does it mean to have a standard deviation of 10? What does it mean to have a standard deviation of 50? And how does that kind of show up on a graph? For later on, we're going to be able to normalize a curve and use a table to do some of our calculations instead of our calculator. So in this section, we study the measure of variance, which will help describe how the data points vary. And I talked about the three most commonly used ones: range, variance, and standard deviation. Range is the easiest one to calculate because you take the highest value minus the lowest value. Last section, we calculated the mid-range. We took the highest minus the lowest divided by 2. That's the mid-range. And that's almost a measure of average. It gives us a rough idea of where we think the average might fall. This gives us an idea of the smallest data point to the largest data point, how large of variance, or how large does each, the smallest to the largest, vary? How many points does that vary? So we're going to look at these two data points for weights of dogs. You see the first picture and the second picture. It turns out both of these have the same average. So we calculated the average in the first picture and the average in the second picture. We get the same, but you can tell there's quite a bit of difference in the second picture from each, in this case, the weight of the dog. So it's going to have we're going to expect it to have a larger standard deviation. So the first thing we want to do is find the mean. This is your first example. For the first list, we have 4 dogs, and we want to find the mean weight. Take the 4 numbers and divide by 4. And if you have your calculator, take a bit of time to hit those 4 numbers and divide by 4. Turns out it's 65.25 pounds. The second list, a range of 15 pounds. For the second list, we have 8 numbers. We add up those 8 numbers and divide by 8 to get the mean, which in this case is 64 pounds. The range is 95 pounds. So the first list, we have the same, very close to the same average, but our range in the first list is 15 pounds, and our range in the second list is 95 pounds.
Wait, I'm looking for the mean in the second one.
You're looking for the mean and the range in both of them.
Yeah, but I don't see the mean. It's 65.
This is the mean in the first one. This is the mean in the second one.
It doesn't give us a
64.
Oh, okay.
It's on the next slide. It kind of didn't have room. Question.
So for the test, say we do, like, we show all your work, like what we're adding up and what we're dividing by, but we misclick.
Yeah.
You still give us
I'm going to
points?
give you points for your work as well, right? Of course, because I want to see, and this one especially, because there's a lot of steps to find standard deviation and variance. First off, you have to calculate the mean. If you calculate the mean wrong, you will have no chance of getting standard deviation right. But I can give you points for knowing the proper steps to that. So we haven't really done anything new at this point. We calculated mean and range. So if most of the values are similar, but they're just one usually high value, the range will make it look like there's a lot more variance than there actually is. If I threw in a tiny dog in that first list, not change the mean too much, but it's going to change the range a lot. So for that reason, range doesn't give us the best approximation of variance, because if I have one outlier, it's going to throw off the range, right? So to take that into account, range is a quick and dirty way to find a measure of variance, but it's not too reliable because you could have one outlier. Question.
What did you say? Standard deviation is the square root of what?
Standard deviation is the square root of variance.
Variance?
Yeah, and that's going to come up later on. So for that reason, we're going to define variance and standard deviation. So this is the process of finding the variance and the standard deviation. Since one is just the square root of the other, you have to find one first, and then you hit the square root button, and you have standard deviation. So the first thing you have to do is find the mean, right? So if you remember last time, we denoted mean as x bar. Subtract the mean from each data value in the data set. So we're going to say xm minus x, well, we'll do it this way. The xm minus x bar for all m in the data set. So that's kind of the math of it. We're going to take every data point and subtract it from the mean. This is kind of like how far away is each data point from the mean. Then we square the difference. Then we take the we actually square all those values. So what we take here, then we add up all the squares together. I'm going to come up with a formula at the very end.
Okay.
And it's also on your handout of the notes, these steps. Then you're going to divide the sum of the squares of the differences of each data point from the mean and divide that by n minus 1, where n is the number of data values. Then you're going to take the square root, and that's standard deviation. So before you take the square root, that's the variance. And then once you take the square root, you get standard deviation. Your formula that comes up later is, I don't want to use a different notation, that's variance. We'll get to it because the process I think is going to make sense once you go through the process. The first thing you have to do is find the mean. So we're looking at these 6 top scores. So to find variance, the first thing we need to do is find the mean, which is 80 plus 73 plus 87 plus 74 plus 83 plus 74 divided by 6. We get 78.5 inches. That's the mean. That's our x bar, right? Anyone have any questions on that, how that was calculated? Right, we did that last time. So now that we have the mean, the next step is going to be find the difference between every data point and the mean, right? So if I subtract 78.5, subtract 78.5, subtract 78.5, subtract 78.5, subtract 78.5, subtract 78.5 from each point. Doesn't matter if it's positive and negative because you're going to end up squaring it at the end. So it doesn't matter if you take the data point minus the mean or the mean minus the data point. Some of them will be positive and some of them will be negative. The positive ones will be greater than or less than the mean depending on which order you write it on. I'm going to go to the next step here. So they went ahead and took the data point minus the mean for the 6 data points, and they wrote it in a table. For the data point, subtract the mean, or the data point minus the mean be listed here. Some of them are positive, some of them are negative. It's perfectly fine. The reason why it doesn't matter is because I'm going to square them. Then I'm going to take my calculator and square every one of them. So 1.5 squared, 5.5 squared, 8.5 squared, 4.5 squared, 4.5 squared, 4.5 squared. Then you add up the sum of the difference of all the data points and the mean squared, and divide by, what number are we going to divide by here? N minus 1, and n is 6, so 5, right? That will give us variance. It's a number that doesn't really tell us much. It says 33.1. 33.1, if we look at the data points, the variance is 33.1. So then the standard deviation is what we want to get to for the next two sections. We take the square root of the variance. So if I take the square root of that, I get 5.75 inches. So the standard deviation tells me, and we're going to get this, 30.25. 30.25, this 30?
Yeah.
No, because we're squaring it.
The negatives in the square.
Yeah. Negative 0.55 squared is negative 0.55 times negative 0.55. Negative times negative is positive. Yeah.
Mhm.
You can never square anything and get a negative number. Question? Here? Because there's 6 data points. And for variance, you divide by n minus 1 data point. It's the sum of x minus x bar over n minus 1.
So that's a lot of steps.
This is a lot of steps, right?
It's like a lot of steps, yeah.
Yes.
This is the variance. The square root of variance is standard deviation. So variance isn't really used except for the fact that the square root of variance is standard deviation. We use the standard deviation to interpret the results. These are time-consuming problems, right? You thought finding the mean was time-consuming. Mode, median, and mid-range was time-consuming. These are going to be on top of that time-consuming because the first thing you have to do is find the mean. Then once you find the mean, you find the difference of the mean to each data point. You take that number, square it, then you add up all those numbers, divide by n minus 1, take the square root of that to get standard deviation. So anytime you can, on your homework, they're going to have you kind of compare two sets of numbers, standard deviation. A smaller standard deviation is the numbers are closer together. A larger standard deviation is the numbers are more spread out. Eventually, what we're going to do with this standard deviation is we're going to normalize all of our data. And we're going to come up with percents of the population that fall within a certain range. And so we're going to have our mean value, and then we're going to have mean minus 1 standard deviation. I think your book uses
It looks like that, yeah.
sigma.
Mhm.
Every book's a little different. And mean plus standard deviation. So this is one standard deviation. We're going to use certain rules. We have the empirical rule, but then also we're going to be able to extrapolate that to a table and find maybe halfway between standard deviations. And we're going to be able to find the area, the percent. The whole area is 100%. We're going to be able to break that down. Most of the data, if you look at area here, is going to fall within the mean for normal distribution, right? And it's like 95% of the population falls between 2 standard deviations. And then you can calculate, well, what about the ones that are just larger than
Is that
the
every
mean.
population 95%? Regardless of what you're calculating?
If it is a normal distribution curve, and most of them are, you can't do it without calculus. This is the approach to calculus is it's integrals. So upper level statistics would use calculus. We don't have that in our toolbox, so we're going to normal distribution and use a table. And the table is going to give us the area, and then we just interpret it.
So if it's not 95%, we're probably wrong.
There's certain markers, but we're going to go like in between those markers, and then we're going to look at the table, and it's going to tell us if it's called the z value. We're going to calculate the z value, then we're going to look at the table, and it's going to tell us this is 32% of the population. And then we might need to add or subtract if we wanted just this shaded region and not this one. The z table gives us all of this here, so we have to take the whole area minus this area. But we're going to get to that. Right now, it's just a number. Then we're going to actually interpret it into a table. Question? No.
No, I was scratching my ear.
Gotcha. So this is variance, and then to find standard deviation, you just take the square root of this number. Be careful on your calculator. Everybody's calculator is set up a little differently. Some calculators, you have to put in your number, then hit your square root. Others, you have to hit your square root, then your number. So you want to be comfortable with your calculator. Here's an almost application type problem. Professor has 2 sections of Math 115 this semester. The 8:30 a.m. class has a mean score of 74 with a standard deviation of 3.6. The 2 p.m. class has a mean score of 74 with a standard deviation of 9.2. What can we conclude about the students' averages in these 2 sections? This is what we're getting to, because there's, probably the middle school approach, find the numbers. Don't think about what they mean, just find them. Yeah, kind of. So if we're looking at the students' averages, relative terms, the morning class has a small standard deviation than the afternoon class. They're closer to that middle score than in the afternoon class. In the afternoon class, they have a lot more range of scores. The range is larger. Scores vary more widely, with a lot of high scores and a lot of low scores that average to a mean. So you can think of standard deviation as how far away are each data points from the middle. The middle is the mean in this case. So low standard deviation would mean the classes are a lot smaller knit. I can pull up your exam 1 and exam 2 scores and show you your standard deviations and kind of compare, were the scores closer together or were they further apart?
Does that mean that it has a lower range, has a smaller standard deviation, or how would you?
Yes.
What would you consider low and what would you consider high?
As far as standard deviation?
Yeah.
It depends on the data. A standard typical curves, 99.7% of the data will fall within 3 standard deviations. These are just so small percent of the population that's too far from the mean. A standard deviation that's small means we're going to eventually get to, that would be 99.7% of the data would fall within this range, versus a standard deviation that's larger means 99.7, we need a larger range. Yeah. So if I have a lot of high scores and a lot of low scores, it's going to be more spread out. Where if all my scores are around this area, it's going to be a little tighter. There's not going to be that much variance. So I can have the same mean, just like with the dogs that all kind of weigh the same, and then the dogs that are some were big and some were small. So there was enough big ones in there to make the average the same as the top score, but the range was much larger. Standard deviation would have been much larger as well, because you're taking every data point minus the mean, and then you add that all and divide by n minus 1. And then the square root has some where it makes sense in this case, in the picture. So
the scores are quite different. In the first class, they're all really kind of close to this mean. And in the second class, you have some high scores and you have some low scores that they average to be the same. Let's look at some of the homework in this section. 2.4,
You're assigned to do the odd from 11 to 25.
Not every other odd this time.
yeah, not every other odd, just the odd one. So here, you can kind of look at this and look at the range. What is the range? 60.
Yeah.
So we have some low scores. We have this one high score, the 61. So that's gonna, affect our range a lot, but it's not gonna do too much to our standard deviation. It'll play a role in standard deviation, but it's not gonna be too bad. These are the number of junk emails this person received in 9 consecutive days. There's 9 data points. So the first thing you want to do on this is to find the mean. So you add up all the numbers and divide by 9. So let's just do this one and then check our answer in the back of the book. So we take X bar is 60 plus 1 plus 1 plus 3 plus 2 plus 30 plus 18 plus 3 plus 7, all divided by 9.
That's 61, isn't it?
Anyone else confirm?
66.
61. Your
At
first
6,
number is
oh,
61.
sorry.
Yeah.
It's
First-
126
the first one.
divided by
It's
9.
61 plus 1.
Yeah,
Okay,
it's 126.
so we got 126 divided by 9,
Which is 14.
which is 14. So X bar is 14. So then if my data points are 61, 1, 1, 3, 2, 30, 18, 3, and 7. If I take X minus X bar, so what's 14 minus 61, or 61 minus 14, that order doesn't matter because you're going to end up squaring them. So we have 47, 13, 13, 11, 12, 16. Right? 4, said minus 11, minus 7. And again, it doesn't matter if the negatives are there. It might even save you not to write the negatives because you don't want to add a negative number when we get to X minus X bar squared.
And then you square them.
Yep. So what's 47 squared?
2,209.
2,209. 13 squared?
169.
169. 169. 11 squared? 12 squared? 16 squared? Oops. 4 squared? 11 squared? 7 squared?
49.
Do you guys see where that's coming from? So now I take the sum.
It's coming from her.
Now I got to add up these numbers together. Some of your calculators might even have a way where you can store a variable, which is kind of handy to do.
My phone has that.
Then you can take all your data points minus your variable and actually square it with your parentheses. So if you were to type in, let's say we store, I don't know, a lot of times it's like this in your calculator as A. You can store the mean, whatever X bar is, as A. And then you can take 61 minus A squared plus 1 minus A squared plus 1 minus A squared, all in one line. Plus 3 minus a squared plus 30 minus a squared. See that? So while you guys are working on the sum, I'm going to pull up a scientific calculator. Do they have a store? So this is not too bad if I don't necessarily store it. 61 minus 14.
You have two minuses in there.
Minus 14 quantity squared plus 1 minus 14 quantity squared. Oops. Yep. Plus, was it 1 minus 14 quantity squared plus 3 minus 14 quantity squared. What was our next number?
2 minus 14.
Oh, did I hit enter?
Yeah.
Too fast with my buttons here. Control Z, it works. Yeah, your calculators don't probably have Control Z, do they? What was our next number? You said
2 minus 14.
2 minus 14.
Mine does.
Oh, does it?
Yeah.
What was our next one?
30 minus 14.
30 minus 14. Next one?
18.
18 minus 14. Next one?
3.
3. Is that our last one?
That one was
Nope.
7.
Plus,
That is a big long number.
plus 7 minus 14. Okay, so you see above here, it has 61 minus 14 squared, 1 minus 14 squared. I can see 9. I have 9 numbers. So I hit enter and it gives me 3,254. Did anyone else get that?
Yes.
Anyone not get that? You would see how easy it is not to get that by hitting a wrong button in your calculator.
There was a wrong number given.
There was?
Yeah, it was 1 minus 13, you had, I think, 196, and it should have been 169. It doesn't matter on what you have up there.
Oh, I see. Here.
So that could have been why.
I got you. Here,
Yeah.
169, not 196.
Yeah.
They're both one together.
Did I write it, both of them?
169.
169.
And then the first 121 should have been
Okay.
169 also.
There we go. Did I have them both? 196?
No, you have both different numbers.
Yeah, then 191.
Oh my goodness.
It's okay.
I don't know why they let me
it's okay.
teach.
We don't.
Yeah.
We know.
Okay, so these two are 169, 169.
Yeah.
And then you take the sum and you divide it by.
So here, what are we gonna? Yes. So we need to divide by n minus 1, and that's probably another common mistake here, students. Will just divide by n.
Divide by 8.
3254. I got that.
Okay, then you divide by 8.
Why don't? But it's an odd number, so we still.
It's n minus 1. It's always n minus 1. For variance, it's always n minus 1. Yeah. I think you're thinking of median
Yeah.
when you take n plus 1 over 2 to find that value.
Okay.
So for variance, you're always going to divide by n minus 1. This gives me my variance, which doesn't tell me too much, does it? Some large number. So I take the square root of that to find standard deviation. Depending on your calculator, 406 is the variance. So I need to hit the square root of that, and I get 20.16. So 20.16. And so what kind of reference would we make from this?
It's a huge.
If there's a large variance in each kind of these numbers, and you could see that when you look at the numbers, 60, 1, 1, 30. 7, 3, 13, 11. Every one of those data points varies quite a bit from one another. Or I could give you 15 numbers that are all 14 and has the exact same mean.
So would that mean, so,
Standard deviation would be 0 because they're all the same. You can have a 0 standard deviation, meaning all of them fall within the median. Or the,
that doesn't happen to all.
no. It wouldn't be a normal distribution if that happened. You have to have some variance. Thank you, guys. All right, so did we look in the back of the book? Did we confirm that was correct?
Yeah, but they rounded, and it is.
Yeah, and I think they might even tell you to round, but maybe not. What did our calculator say? Did they just say 20?
20, no, they said 20.17.
20.17?
If we
So
round it, we're gonna make
20.1, that's fine. I mean, honestly, your homework is for your benefit, not real. I mean, I look that you completed them and look at your work and kind of give you points that way, but I don't go down to the details and take off. Oh, you didn't round on this. I mean, think about if I did that to 30 students. Well, it would make sense if I would have given it back to you before the exam, but your homework is due the day before the exam in that case. So by the time I grade it and give it back to you, you wouldn't get that feedback for the exam. The exam's 15% of your overall grade. So that's really the meat and potatoes of can you do it on this test versus can you do it when you have multiple devices. There's standard deviation calculators online where you type in all the numbers, hit enter, and it'll give you the standard deviation. So you can check yourself that way, but also these are odd. They're all the answers in the back of the book. So if you're not too sure the back of the book is right, you can plug it in one of those. And all it does is just calculates the mean because these are just numbers. It just plugs it in something and spits out your standard deviation. You could see here standard deviation might be higher because the numbers are higher. So standard deviation also kind of looks at your data points. So if I have numbers in the thousands, I'm going to expect my standard deviation maybe be in the hundreds. But if I have numbers in the hundreds, my standard deviation is probably going to be in the tens. So you can't really compare standard deviation from standard deviation unless you normalize it. And that's what we're going to end up being, to normalize it, where standard deviation or the median and the mean are the same at 0. And then numbers to the left are negative because they're below standard deviation or below the mean. Numbers to the right are positive. So that's a normalized curve. So here it doesn't mean too much because you have to think of the data point. The data points are small, your standard deviation is going to be small because that's what you're looking at. But if they're really large, your standard deviation will be large, but it's going to be all relative.
And then it's gonna, like, if they have a large deviation among a large number, like that deviation could be small.
It could be
compared to
relatively, yes, exactly. And that's what we're going to get to when we look at normal distribution curves. So at this point, we're just calculating it, right? So here in the 200s, our standard deviation is going to be higher than number 17, simply because our numbers are larger. So at this point, comparing one standard deviation from another standard deviation is not really fair because you're comparing apples and oranges. So there's a way that we're going to end up doing. And see, this is 12.4, 12.5. We're going to get to measure of position. Where does this kind of fall on a curve? And we're going to look at percentile rank and data values. That's within a certain amount of data value. So all this we're going to say is, okay, now let's look at a data set and let's see how one value of the data set ranks within the other numbers. And then in 12.6, we're going to say, okay, let's compare this number in this data set to this number in this data set. If you think of it, I went to a class, a high school, had 60 in my graduating class. My husband in high school had 5,000. I was ranked X, he was ranked Y, and you really kind of compare that what that meant. So there's a percentile rank. You know, third in your class could be the same as 30th in a class of 5,000. Does that make sense? So we're going to look at percentile rank. We're also going to look at a lot of times you rank yourself. I'm first in my class or I'm sixth in my class. What does that mean? If there's 10 in your class, or if there's 10,000 in your class, what that means and how many people, is the top 10%. If you only have 60 in your class, the top 10% is the top 6 people. But if you have 100, then it's going to be different amount there. So we'll look at percentile rank. We'll also look at dividing the data into 3 distinct regions: the first quartile, the second quartile, and the third quartile. So really, there's 4 quartiles, but there's only 3 dividing points. Right? Everything lower and then in the middle. We look at the quartiles there. So that doesn't quite get us. Eventually, we're going to be able to draw. And this book doesn't stress it, but if you guys done box and whisker plots, if you've ever had standardized tests, or if you're going to be a teacher and you're going to give your class standardized tests, you'll have a box and whisker plot a lot of times that will give the data. And this will be the mean, and then this will be one standard, or this will be the top 75% of the class, or really the top 25. This would be the top 50. This would be the top 75. This would be 100% of your class. So you could look at a box and whisker plot, and they can vary quite a bit. And yeah, you're able to kind of look at lower 25%, lower 50%, lower 75%, and all of it. So that's what the first quartile, Q1, Q2, and Q3 represent. So these are data values, these are numbers, and we're going to calculate them. It happens to be the median of the data points in the upper half. This happens to be the median of the data points in the lower half. This is the median of all the data points. And we can look at measure of position. So that's what we'll do in 12.5. 12.6 is actually getting to the normal distribution. So being able to compare data sets to data sets. 12.5 is just looking at a data value within one set. Where would this data value fall? Percentile range. You guys, proficient, nearing proficiency, needing work type thing, and they'll say, out of the people that took this test, you're the 90th percentile. So it depends on what everyone else scores, kind of where you fall. The MOGIA is actually working on this and trying to find a passing score. They're looking at percentiles. So they're saying if everyone takes it, maybe there's a really great group that takes it, you could get the same score and not pass one time as you get a score the next time, the exact same score the next time, and actually pass it. Because it depends on how everyone else does around you. So yeah, we're leading up to this normal distribution, and you'll have to memorize. This is where standard deviation comes in. The empirical rule says your standard deviation for your data set, because everyone's data set standard deviation is going to be different. 68% of the data is going to fall within one standard deviation. So 38 or 34 below and 34 above. So 2 standard deviation, 95% of the data points will fall within 2 standard deviations. So this shaded region is about 13.6, this one's about 13.6. And then 3 standard deviations, 99.7. So we're going to use a table that is given in your book. See if I go to last semester's. Math test.
Ms. Bamer,
Yes.
while you're looking that up, when we do the variation, after we add all the numbers together, if we come up with, like, on number 13, I came up with 716.6. So did we just round that to 717?
You can, and that's in your homework. Your answers the back, they might round it a little differently. That's fine. On your exam, I'll be specific, round to the nearest decimals, or round to the nearest 3 decimals, or something like that.
Okay. All right.
So this is the table that we're going to use when we talk about a z value. So the first thing we're going to have to calculate where our data falls. That's going to correspond to a z value in a normal distribution. And then this area is always given here with the corresponding z value. So if our z is 0, our area is 0, meaning I'm 0 from my mean value. So 0% of the population falls 0 from the mean.
And does Z vary, or will Z always be?
Z will be calculable. You can calculate Z. The formula, we'll calculate it, look at the table, look at this area, and then it might say what % of the population falls to the left or to the right. What % of the population is taller than 5 foot? Well, we look on a normal distribution, the average, the standard deviation, we can find the Z value for 5 foot, and then we're going to add up all the areas to the left of that, or all the areas to the right, depending on the question's wording.
Okay.
So 50% of the population falls on this side, and 50% falls on this side. So depending on if I want this area, and it helps to kind of shade these in, and we'll go over that, but that's when we normalize it. So 12.5, we'll be looking, how does data points fall within a certain set of data points? Is it in the 10th percentile? Is it in the 90th percentile? Where does that fall in the chart? First quartile, second quartile, third quartile, or fourth quartile? And then you have this Q1, Q2, Q3, which breaks up the quartiles. 12.6 will say, okay, how can we compare two different data sets? We can normalize them and then be able to make a comparison with what % of the population falls within this certain range in this data point, and what % of the population falls within a certain range in a separate set of data points. So the normal distribution is really helpful when I'm comparing apples to oranges. And that will be, I believe, 6, the last section we cover in this chapter 12, 5 and 6. So I know we kind of went over a little fast today, but it all depends on if you can push the right sequence of buttons in your calculator. I will test, probably on the test will be 1 standard deviation, 1 variance on there. And then some others might ask, what's the process? How do you go about finding it? If you could write that out. Because, anyone can punch a series of buttons in their calculator, give it enough time, but I don't really want to test if you can push the right buttons the right amount 500 times. So.
And the sentence, I don't know how much.
Yeah. Yeah.
Is a sentence like this okay, or do you want more?
That's fine. Some of it will be, it'll be
Because
very.
some of it be like, some will be closer.
Yeah. Yeah, but be careful. Yeah, because if your data points are in the 100s, you might have a standard deviation of 20, but it's not going to vary that much.
Yeah.
But when your data points are in the 10s and 20s, and you have a standard deviation of 20, it's going to vary a lot. So that's where the sentence comes in.
I was just making sure that I was okay.
But yeah, that's fine. You too.